Thanks, everyone, and hopefully you're not tired of me already. I presented in the morning, but I have another project to share with you today. So that's an unproprietary outright performance concrete for precast bridge joints. It's part of our work through the ABC UTC, the Accelerated Bridge Construction that's housed at FIU. And this is another student, was the twin brother of the student that I presented the work earlier, like in the morning through the ACI project. So that's another Abukifa here. And what I will do today, like in the next 15 minutes, this is actually a multi-institutional project that's going at the ABC UTC. We are trying to look at, tailored or engineered type of non-proprietary UHPC for specifically for ABC connection. So let me start by what type of ABC connections we are focusing on here. These are the, the one you see on the left is the most popular application for accelerated bridge construction in the US, pretty much like we're using UHPC for field joints for decks. But also in California, recently they used UHPC for seismic connections as well. So these are just two types. At UNR, we did a lot of work on both, developing non-proprietary UHPC specifically for Caltrans for this type of joint, which, we did some anchorage, testing specifically for large diameter bars up to number 10. And we developed an equation for the anchorage lengths. Then we use this, for even 0.4 scale columns. And we, tested them to make sure that the column will, develop the plastic hinge in the column as intended. So that's one example I'm not going to talk about today. But the other example or the other type of connections we are working on is the non-seismic or the bridge deck, joints. And again, I'm starting here from the end of the project, before I go to the material part. This is, what we eventually got to is that, we had 9 pairs of precast sub-assemblies of bridge decks with transverse and longitudinal joints with different design and different detailing and different materials. So we, I'm sharing here one example here just to show, the comparison between a non-proprietary and a reference commercial UHPC. Again, the idea here, we know that commercial UHPC works great, but we just want to, for research options and for the bigger benefit of the community, wanted to show that other, options would work as well. So that's a head-to-head comparison, exactly same dimensions, of the specimens. The only difference is that we used non-proprietary versus, commercial UHPC in the mix in the joints, and we showed that the non-proprietary or the engineered UHPC could lead to a good behavior. So that was the end of the project. But let me go back now, a year or two before we reached this stage, where we wanted to develop the material itself and see what type of non-proprietary UHPC would work for this application. So this, as I mentioned, earlier, it's a multi-institutional collaboration among the 5 consortium members of the ABC UTC. This work was led by the University of Oklahoma in terms of the basic or reference, non-proprietary mix for the UHPC, and then each of the universities took on a separate role. University of Washington, for example, they are focused, they focused on the shear panel testing. Here at UNR, we did these, full scale sub-assemblies of deck joints, as I mentioned. But along the way, we found that it's beneficial to do some side material study, which I'm going to share with you today. So we got the material. Basically, our objectives were to get the materials from and the basic reference design from Oklahoma, and we wanted to reproduce the exact non-proprietary mix using not only we are using a different team, different mixing procedure. Everything is different because that's a separate a team from the original design. So we wanted to see the repeatability and the reproducibility of this mix. But on top of that, we also used and sourced materials there locally from the western part of the country, from Nevada and from California, and wanted again to study how the material sourced from the western side of the country would lead to comparable results or not from what Oklahoma designed for the basic or the reference one. So we wanted to study or investigate the effect of material sourcing and variability, specifically the fine aggregate type and particle gradation, which I will show. And the other thing is, even if we are using the same material that our collaborators at Oklahoma used, can we reproduce it, if we are using different people, different mixing, and see just the human factor, does it reproduce or not. And then we did a full mechanical characterization for what we call the ABC UTC like non-proprietary UHPC mix in terms of compression, flexure, and tensile properties for those who are interested, to use these results maybe for like modeling purposes or assessment of relevant analytical equation and so on. So that's the non-proprietary UHPC mix. Again, Oklahoma, like the University of Oklahoma, like Royce Floyd is the one who, championed this effort. And this is the mix that they started. And you can see here we have the typical components, like the cement, we use like silica fume and slag here. We use like sand. And the sand is, like a big component here, the fine aggregate, which I will talk about. And then we used steel fiber, 2% by volume for the basic one, but we also used 1% as well to show that you can even go, like with less steel fiber for these applications, for specifically for the ABC, ETC, like bridge deck connections. So this is some general information about the mix. This is how you see, like the like close to final state before we furnish the material and so on. So for the material variability, these are the sources that we used for our material. So, like University of Oklahoma, as I mentioned, they are the ones who started the mix design, and they provided us already with the materials that they have used. But in the meantime, we try to source similar materials locally here in the western part. So the cement we use, like a Nevada company here, the silica fume, and the slag, we got them from Sacramento. And, the main part is the aggregate. We used actually different types of aggregate here, but I'll just focus today on the crushed aggregate that we have used, because we try to use sieved and unsieved, and again wanted to see if this could lead to similar results or not. So for steel fiber, as I mentioned, we varied this as well, 1% and 2%, not because we are trying to walk away from like high steel ratios of steel fiber or anything, but we want to show that steel fiber can be one of the components that can be optimized or engineered based on the application. So here in this example here that we did in this testing, we tested, like for example, using the non-proprietary UHPC, used 3 different joints for the transverse field joint as a sample here. And we wanted to see if we were to use 1% instead of 2%, from just some of the back of envelope calculations and stuff like that. We said that, okay, maybe this would come as the cost of increasing the width of the joint a little bit. So instead of the traditional, 6-inch width we use for the joint, we went here with 8 inches. Not really a big difference, but we wanted to make sure that at least for 1% we have a little bit more lap length. And we wanted to test the 2 of them. And you can see here that the 1% and the 2% concretes, almost have identical behavior. So again, I'm usually trying both the material and the structural results together to show the motivation. Why would we, characterize the material with 1% steel fiber as well? So that was the steel fiber. The other part is the aggregate type and the particle grading. Again, UHPC, and I have heard this from, several presentations today, it's all about the particle packing theory. So we wanted to show, again, on purpose, we are not after a 25 KSI, like high-end UHPC. We want a practical mix for a specific ABC type of application. So if we are not even going to do sieving for the sand, and you have seen here, this is, very large particles, versus a sieved sand that we sourced here at in the Nevada part. And then that's the fine sand that we got from Oklahoma, how these 3 would compare. So we did this as well, and putting all these things together, we had 5 batches that we tested, 2% and 1% steel fiber, using our non-sieved and sieved aggregate here from the Nevada region, and then we have the Oklahoma one, the materials that we got from them for reference purposes. And then we started our mechanical characterization campaign. We did compression, flexure, and tension. Again, you have been hearing about tension from the morning. There is no standard test yet. We are not actually after a standard test in this specific objective. Our objective is not to really, do the best tensile characterization, but rather, do a comparative study. And if we have 5 batches and we do the same test for all 5 different types of concrete, it's just a comparative assessment that we are doing here, as opposed to having a specific test, that we know that this is the maybe standard results that you would use for approving this mix. This was not our objective from the testing here. So we went with the dog bone, samples with a 1x1, cross section. And, the standard flexure test, we did the 3x3x12 and the compression, the 3x6, cylinders. And we wanted to do the full, stress strain characterization for all these type of tests and see how this would compare to analytical equations in the literature. Most of the analytical equations have been verified for proprietary and high-end UHPC. So we wanted to see if these things are like, valid for non-proprietary mixes or like lower-end type of mixes as well. So we started, like by the flow, especially that we had, like the, you can see here, that's the unsieved one. All of them, like in terms of meeting the ASTM 1437, like they are acceptable in this range. But like you can see that there's some like variation in the flow, which is expected. It's again, if you have this, we see that this might have the lowest, like flowability, but it's still acceptable and you can furnish it in a field joint. So this was our, target here is to meet the required or the minimum required, like flow as well as other mechanical properties. Flow is not mechanical, like if you can argue, but like flow and other, like mechanical properties as well. So that was our target here. They have the most practical, if you will, the most practical, convenient mix that can work for this type of joints. So we did the compression test. These are some of the results here. Again, like for the strength gain. And we are, like around the 120 megapascal, which is the 17-ish KSI that, again, is common for non-proprietary UHPC. And it's not, as I mentioned earlier, it's not like a high-end 25 KSI type of UHPC. It's more like a practical low-end one for ABC joints. So this is like the 5 different batches. Here you can see here, that's the effect, like this is the 1% steel fiber. These are the 2% steel fibers. So the Oklahoma versus the 2 from Nevada aggregates didn't really have that much variation when it comes to the compression gain or the strength gain. These are the, like full stress strain curves that we try to get with, like I'm showing samples here. Of course, like this project was happening like last year, right around the, like the COVID shutdown. So you will see a lot of weird times here for testing. It all depended on when we were allowed to go back to use the lab and so on. So there are some results that we were able to get at standard times, like 28 days or so. Some specimens, we couldn't, like test them at 28 days and we had to wait until we were back in the labs. So for the compression, for example, the stress strain ones, we were not able to test these until like almost 240 days or so. But, like we have done this and we get at least the early part, like, this is non-confined UHPC and we didn't really care that much about capturing the post-peak behavior. So we just wanted to at least get the initial part, which has to say something about the Young's modulus indirectly. The equations, for example, what, like Ring Reveal and the folks at the Federal Highway has proposed for, like predicting or estimating, like the full stress strain relationship in compression for the up to the peak. So we show that this, works for non-proprietary UHPC as well. And we did some assessment for the equations here. We got also, like from the flexure test, we wanted to make sure, again, when we compare these 5 together, like the standard thing is that we are looking at, these are in, like in megapascal, like I don't have the plots, like in the KSI units ready, but, like this is like the, I think this will be like 7 or so, like KSI in terms of the, no, not 7, I think. This is 4 KSI in flexure and in direct tension, like we got to 7 megapascal, which is, I think, 1.2-ish, like KSI. So the values are there, and we tested this at 7 days and 28 days. You can see that, like in tension, it's not like compression. You don't really get a lot of like change. So the 7 day and 28 days, that change, I think the increase in the tensile strength was, I think, was in 20% or so, which is, like expected again and matching what we have seen in the literature, because the tensile behavior has to do a lot with the steel fibers as opposed to the UHPC itself or the cement, like
Mohamed.
Yes. Sorry. So like these are just some of the results here. Again, what did we wanted to show here? The 1% and 2% obviously will have different results. We wanted to show that the trend in general, if we just focus on the very first part, you will see some part of, like strain hardening, but, we are plotting it all the way up to 5% strains to show that, like the ductility is there. And so again, the idea here is to provide just some sample, like full stress strain curves for this material using different batches for those who would like to pick these later on for modeling purposes or analytical assessment. So, like let me just wrap it up here with some concluding remarks. The basic characteristics, of the mix designed at Oklahoma University or University of Oklahoma, like based on the Midwest and South US region materials, was successfully reproduced and replicated using like full independent set of materials and even different aggregate types from Western US, which is encouraging for all these developed, or emerging non-proprietary mixes. We can use different materials sourced from different places. And so this is one promising, observation or conclusion that we have here. The developed non-proprietary HPC with sieved and non-sieved sand both met the minimum, like compression strengths requirements as far as the 117 megapascal, the very lower end that we were targeting. Flow, tensile properties, all, were met. So having actually an unsieved sand is not really bad. We know for sure that this is not ideal in terms of the optimal particle packing, but at least for practical purposes, we showed that it works. The flexure and tensile behavior both showed all the trends that we are looking for in terms of, the initial strain hardening, and then, you have the ductile behavior. So what we did as part of the ABCTC, and again, this is just only for this project, we don't want to make, bigger conclusions yet, but at least based on what we have seen in this recent collaboration among the ABCTC, we recommend at UNR, that using 1% steel fiber and non-sieve, sand would just strike a balance between the acceptable mechanical behavior and, the cost. Because, less work for sieving means less work, especially if you are scaling this up for large quantities. Less fiber, of course, will mean less cost. So there is room to engineer, UHPC based on the application. Not, again, every application. If I'm doing columns like what I was doing in the morning, I would use a different type of UHPC. But this is to leave everyone with this, thought that it's about time to start engineering even our mixes further based on the application. So with this, I would like to thank you and answer questions if you have any.
Okay, thanks a lot, Mohamed. Thanks for your talk. And as for the previous one, it's interesting to say, and also for presentations we have seen in the first session, to say that, there is not a unique UHPC. You can have different performance requirements, which will turn into different compositions. And most important thing is to have locally offset constituents, because we are speaking about sustainability, but sometimes we forget that the transportation of the raw material to the batching plant and so on also have to be considered when assessing the overall footprint